Well, good afternoon and welcome to the Computer Security Seminar, CERIAS seminar from Purdue University. Our speaker today is Abby Bargov-Spancel. Sorry.
That's all right.
She came to Purdue in 1999 as a sophomore and just in the last couple of weeks has defended her PhD thesis. And she's going to share from her thesis with us today. The title is Protocols and Systems for Privacy Preserving Protection, that's probably hard to say real fast, of digital identity. Abby?
Thank you. So this is a whole lot because it covers a lot of very interesting related topics. And I'll try my best to go over most of them as carefully as I can. And please feel free to ask me questions during the presentations, if you will. Okay? So I'll be talking about, and yeah, just the last person. If at any time I start mumbling and you cannot hear me, let me know. Okay? Thanks. So I'll be talking about protocols and systems for privacy preserving protection of digital identity. So this is my main thesis research. And it has been motivated by a real-world problem of identity theft. Now, what is identity theft? So identity theft is a crime in which an imposter obtains identity information and uses it for its own personal gain. So how many people here have known identity theft? Nowadays, there's a lot of commercials and stuff. Anybody? So yeah, almost half, maybe more. So there have been increasing number of data breaches. You've seen some of the TJX cases last year. This year, only till last month, yeah, there have been 308 breaches, and a lot of people's personal information has been compromised. Now, with all this nice information in the hands of attackers, there has been a lot of liability, you have financial losses, but at the same time, you have a lot more victims of identity theft. So you can think of financial fraud and all that, but there are other very severe impact on victims with anger, fear, even having criminal records because of this type of thing. So to this extent, the main goal of my research is to provide strong verification techniques of this to avoid misuse of this identity information. So to this extent, I present some protocols, cryptographic protocols to do multi-factor verification, which is a form of strong identity verification. And then I go ahead and talk about biometric and history-based identifiers. So these identifiers are increasingly becoming an integral part of one's identity. But let's first look into some of the basic concepts of identity. Okay? So what is digital identity? So mostly in the beginning, one can think of identity as NIMs. This is how we started. We take any string. I could choose a name like Homer07 and go to a web page and chat as Homer. So those are NIMs, nothing to do with my real-world identity. But then there are identifiers such as strong identifiers like social security numbers, which uniquely identify you in the US, and weak identifiers, which can put you in a group of people. So related to digital identity, there's an aspect of ownership of identity. Now, having identity stored in all sorts of places, it is probably not very clear who is the owner of a digital identity. For example, if I go to a clinic and I get an X-ray done, it is not clear if this X-ray report is owned by myself or the clinic. So in my work, I consider the owner of a digital identity to be the individual to whom this attribute has been issued to, or the individual who is authoritative of making the claim. Okay? So identity verification then becomes the verification that the claimed attribute is actually owned by an individual and is valid. And this identity verification can occur with various types of assurance levels. And the assurance is basically the confidence about the truth of ownership of a particular identifier or validity. For example, if you go to a shop and you present your credit card, then the shopkeeper may check if you actually own the credit card and also runs it through and checks with the issuer if it is valid. So note that this identity assurance exists with or without the linkability to the real-world individual. Now, this is not very intuitive, so note this example. So if you have this first example, which has the claim that a social security number is valid and is owned by a NIM Homer07, who is the real-world individual Bob Smith. Okay? So here there is a claim which can be of strong or weak assurance, but it is very well linked with the real-world individual, Bob Smith, right? But you can also have claims of strong assurance that a particular NIM, Homer07, is a US citizen. So here I know for sure that this entity called Homer07 on the web, whom I do not know who it is in the real world, is a US citizen. So in our work, we consider the cases where we have strong assurance with or without the linkability to the real world individual. Okay? So now we look into what are identity management systems. So this identity management systems have existed for a long, long time. They try to achieve a variety of tasks related to identity provisioning, directory services, auditing, single sign-on, access control, and so on. So governments and businesses are using these identity management systems to provide services like health, commerce, collaboration, and so on. So my aim over here was to show the complexity of these identity management systems. These are big systems. So I went on to the web and I was trying to retrieve a bunch of examples. I saw more than 200 companies with one or more products. So over here I just provide some of the initiatives. The number of standards also provide some kind of evidence that these systems are growing, are of growing importance. So you have standards such as Liberty Alliance and W3C and so on, which provide some kind of standards to how this message exchange happens in identity management systems. Okay? So given that these identity management systems are big, complex systems, and they have a lot of other issues with relating to laws, business requirements, and so on, my research focuses more on the research challenges related to misuse prevention of identity in such systems. Okay? And we take a holistic approach in that we look at the whole life cycle of an identity and see what can go wrong in each step and how to protect against misuse. So the very first step is the issuance of identity. And it goes back to a discussion that Ian and I, we were discussing this morning, that one could potentially have a valid passport, but if it was issued to a wrong person, regardless of the fact that this passport cannot be forged or it cannot be duplicated and whatnot, it has just been issued to the wrong person. So if the issuance is wrong, then the rest of the system can not rely upon such an identifier. So the issuance is one of the most important things that we look at. And then it comes down to having various types of flexible types of enrollments that we need and calculate the assurance levels associated with that. So online enrollment versus in-person enrollment and so on. The next step is actual usage of identity. So at this point, it is most important to prevent against misuse. So related to that is the multi-factor validation. So whenever a person is trying to use an identifier, he is able to provide other proofs of identity. At the time of providing the strong verification, it is important to make sure that you're not disclosing more information than needed. So here I want strong assurance that this person is who he says he is, but at the same time we want to ensure the privacy of that individual, in that he is not required to provide more information than that is needed for the service. So minimal disclosure is one of the important aspects. Then is the use of biometric data and history-based data, which I just mentioned, being an integral part of one's identity. So you can think of it as what you have is a part of your identity, who you are is another, and also what you do also becomes a part of your identity, which is the history-based data. Okay? And the next step is also the modification of identity. So I enrolled it securely, I'm using it all right, but then the modification has to also make sure that there is no malicious entity trying to tamper with it. And finally, the revocation, where we need flexible and efficient types of revocations to be able to manage such identifiers. So the key problem that we are looking at is the misuse of identity attribute. So this happens when an adversary who does not own an identity attribute successfully uses it. So we do have a lot of solutions like phishing prevention techniques and so on, which look at parts of the identity usage. But at the same time, it does not look at the whole life cycle of how this identity gets used. So it's as secure as the weakest one, right? And most of the identity management systems do not consider various types of identifiers, as I mentioned. So what is really needed is strong verification of identity attributes in the whole identity life cycle. So to this extent, I present privacy-preserving multi-factor verification of identity attributes. So this is a mouthful. What do I mean by this? By multi-factor verification, it means verifying that an individual owns an identity attribute by requiring proofs of ownership of other associated identifiers. To understand this, let's take a very simple example. If you go to a shop and you're trying to use a credit card, the shopkeeper may ask you for driver's license or some kind of photo ID associated, and they check if this is the same name and the same photograph and so on. So that is a multi-factor aspect. The second is the privacy preserving. So in the example I just gave you, the shopkeeper comes to see your driver's license, your age, maybe your state of residence and so on, which is not really required to verify that you own this credit card. So we want to preserve privacy, and therefore we use this concept of proof of identity, which is essentially a cryptographic token bound to the individual. And when it comes to identity attributes, we also consider various types of identity attributes, which is the biometric and the history-based. So very briefly, I'll go into the key main properties of the system. So we want some security properties, some privacy. We want the biometric and the history-based support. So we show what we really mean by these security and privacy properties in terms of some very basic properties of confidentiality, non-repudiation, and so on. These are some very strong properties that are needed in the system. And to achieve this, we have a framework which shows what are the key entities and how they interact in the whole life cycle. And then we have protocols to do zero-knowledge proofs used in the multi-factor verification, and then systems which show how to integrate the biometric and history-based identifiers for such multi-factor proofs. So just one slide on the framework. I don't go into the details on that, but the framework consists of three main entities. First is a principal, which is like any user using the system. For example, Homer07 is a principal who's using the system. Service provider is like eBay, Amazon, like any kind of service provider providing services. The registrars is a new type of entity, which is, I got a mail. So the idea is that these registrars establish and maintain identity commitments. So these commitments are there to are required to do zero-knowledge proofs, as we will see some examples. And now we just jump into the aggregate zero-knowledge proofs. The idea of these zero-knowledge proofs is to have a way to prove that you have multiple strong identifiers without revealing them in clear. Okay, so zero-knowledge proofs have been there for a long time, but the key aim over here is to provide mechanisms which are efficient and flexible for the purposes of multi-factor verification. So the tools that we use Peterson's commitments. So I'm not going into details. This would take forever to go into each one of them. But if you have any questions, let me know. Okay? So we use Peterson's commitments. The key thing to see here are those M and R in red. So the M is essentially the strong identifier, like the credit card number, your social security number. And R is a secret. R is a secret that is associated with the strong identifier in this particular commitment. And G and H are public parameters. So we also use bilinear maps in our protocols, which are actually used in Bonnet's aggregate signature. So the main idea over here is that multiple signatures can be aggregated into one signature, and it can be verified. Multiple signatures can be verified at once. And the basic zero-knowledge proof protocols we use is from Carmanish and Stadler. We use their approach and even their notation. So here you see this fancy formula. All that it means is that the user is providing a proof of knowledge of two identifiers, alpha, beta. By Greek letters, we just identify those identifiers which are secret to the user, and which is of the form C equal to G to the alpha, H to the beta. So the key idea is that I can prove that I have alpha, beta without really revealing them in clear. Okay? Just to put it in perspective, like the registrar is the one which is using, which is storing what is called the identity record. So this identity record consists of commitments and commitments of the form which I just showed you, and the signature on these commitments. Note that the registrar never has the value of these strong identifiers in clear. It doesn't know the credit card number, it doesn't know the social security number, but they are just stored in this particular form so that the user can prove ownership of later. And also, along with these commitments is stored the assurance that I'm sure that this particular identifier is valid or not, that is validity assurance, and then the ownership assurance, which talks about how sure am I that you actually own this attribute that you're claiming. Okay? So let's look into some simple examples of how these zero-knowledge proof protocols are used. So I'll go through some instances. So here, consider the case that Homer goes on to ask a service provider for a car insurance. Now, to get the car insurance, the service provider requests Homer for the clear values of the credit card number, the driver's license number, and the social security number. So Homer does not only want to provide these values in clear, he could potentially steal these values and provide it, right? So instead of just providing them in clear, he also wants to prove that he has the secrets R1, R2, and R3 associated with these strong identifiers. So he does some kind of an aggregation. He computes this aggregated signature and some other numbers used in the zero-knowledge proofs. Okay? So when he sends this in some token, so these are the commitments, the capital M1, M2, M3, along with the values of the strong identifiers, then they engage in a proof of knowledge. So in the proof of knowledge, he basically says that he provided these credit card number, driver's license number, social security number, but he also knows all the secrets associated with them. And remember, these secrets are never revealed in clear. Okay? But he can prove that he knows the bound secrets of each of these strong identifiers. So once he does that, the service provider can potentially verify the signature, the aggregate signature, and basically our techniques are very efficient. So you can just check one thing and you've checked the 3 strong identifiers that they requested. And if this signature is okay and the proof was okay, the Homer gets a service. So now let's consider another scenario where Homer is a Secret Service agent. Okay, so he has a reason to hide the kind of commitments that he has that he's enrolled. So and let's consider the government is the registrar. So if Homer has enrolled some commitments at the government, that means he's a government employee. So to request, while he's requesting for a hotel discount in step 1, the service provider says, okay, give me any 2 proofs that you have enrolled at the registrar. So at this point, Homer does not need to say that I enrolled my Secret Service agent number and something else, because just the fact that he enrolled those numbers reveals more information than that is needed. So what he does at this point, he just takes the signatures. He doesn't take the commitments, and he aggregates these various signatures in this particular manner. So he takes the cumulative signature of any 2 signatures and also prepares his secrets associated with those signatures. He sends this aggregated signature to the service provider, and now look what happens. In this particular proof of knowledge, not only is a verifier checking that the signatures are valid, but also that the person who is presenting it has all the secrets associated with it. So in this particular proof, in one step, he checks that he knows all the secrets associated with it, and each of these signature is from the government registrar. If all of this is correct, he gets a service. So to make this scenario even more interesting, let's consider the case when the service provider needs any proof that he has enrolled with the government. In this particular case, you have not only can Homer not provide a signature, he can provide a signature in a hidden form such that if he goes and proves the same thing to the service provider twice, these various things cannot be linked. So he stays unlinkable. So the first step is that he hides the signature. A very simple way to hide it, he just chooses a random and creates delta. Now, instead of sending the aggregate signature, he sends this delta to the service provider. And now the service provider and Homer engaged in this proof of knowledge, where he shows not only that the signatures is valid, but also he knows the secrets behind those signatures. So in between all of this, basically the key thing that we get is that individuals can prove that they have certain strong identifiers associated with each other, and also do it efficiently. So very quick, analysis is analysis comparison. If you see that the amount of exponentiations that we need are constant for provers, which is very nice because it's the provers that are constrained with devices and stuff. So as compared to other techniques which do not use aggregation, in our case, the T over here corresponds to the number of identifiers being proven. So these are the factors in the multifactor. So we do not depend on that amount, the T, and the provers can efficiently create these proofs, and this verification can also happen quite efficiently in most cases. Others, it's comparable. Another thing which you may probably not see if you haven't seen the protocols is the storage requirements. In most of the current aggregation techniques in zero knowledge, they require the kinds of combinations to be predefined. In our case, we can combine it in any form during the runtime, during verification. In the other cases, they require the user to store all sorts of combinations. And if you can think of it, there will be exponential number of those combinations if you want to store all sorts. So that is very nice. So I know these are like deep crypto things, and it's hard to get into it at once. But if you have any questions at this point regarding the crypto protocols, I'd be happy to answer. Or you can think of it and we can talk about it in the end. So at this point, we'll switch gears and go to talk about some of the biometrics and how they integrate in such cryptographic protocols. Biometrics have been there for a while, and they have been investigated in several ways. But integrating them in cryptographic protocols is hard, because if you take a biometric and you record it twice, it is most likely that those two recordings are slightly different. There's a certain amount of noise which does not make it. It's not straightforward to use this biometric reading for cryptographic protocols. What is traditionally done is that the biometric is captured, and certain features are extracted. So once you extract the features, a template is created. A template is essentially digital encoding of a biometric. And then it is, at the time of enrollment, it may be stored at the client or the server. Different problems exist based on where it is stored. And at the time of verification, there's a probabilistic matching. So it is matched against the stored template. Okay? So one of the biggest problem here is the template itself. Like, regardless of where you store it, if this template is compromised, then you can potentially misuse this biometric, or you can link it to other databases where you can retrieve more information about this user which was outside the intended purpose. Okay? So one of the things that has happened recently is to generate keys from these biometrics. So the main idea behind generating keys is to first take the biometric and convert it into some kind of a bit string. So this bit string should have two specific properties. Okay? The bit string should have large inter-class variation. It means that you and me should have different bit strings. We should not generate the same bit string. So it should have large inter-class variation and small intra-class variation. That means that if I record a bit string twice, it should be close to each other. This closeness is really determined in the second phase, where you have a bit string and you use some metadata and boil it down to one key. So if two instances of the bit string are similar, so it's from the same person, then the same key should be generated. Okay? In our system, this is the main flow. In the first phase, what we do is we take various types of biometric images, and this is like face, iris, fingerprint images, and we use singular value decomposition. This is a technique to extract the most significant features of an image. Many of you might have done it in linear algebra. And basically, you do the singular value decomposition and extract the main feature vectors of this particular biometric. So a person who records his biometric twice will have similar this biometric key hash vector. At the time of the second phase, what happens is that you take this hash vector and use a classifier to classify this particular hash vector. And in this whole process of classification, we generate a particular key. This biometric key is the strong identifier that we used in the original the zero knowledge proof protocol. So we commit this this biometric key along with another random, which is used again in the zero knowledge proofs. So let's go into a little bit more in depth of how this particular hashing is done. The procedure is rather interesting. If you see, the input image is taken, and then various aspects, the various parts, sub-images of the original image is taken. So these squares are selected pseudo-randomly based on some secret. And each of these squares are associated with, are basically converted into a matrix, which is used to extract the most significant features, which are called the eigenvectors. So we take the largest eigenvectors for each of these sub-images. Then these are pseudo-randomly combined to form a secondary image, which is again used with the singular value decomposition to get the final hash value. So just to understand what does this SVD mean, it's basically for each image, it's broken up into two orthogonal matrices, UI, VI, which is basically kind of taking the most significant features of AI. So at every point you can think of filtration, like you take the best parts of an image, you combine them together to form the secondary image and do the same process again to get the final hash vector. Now this hash vector is a point over here in this classification model. So this classification model has a lot of users, and this one point corresponds to one hash vector. So at the time of key generation, what happens is that this particular hash vector is ranked, and based on the confidence degrees of a support vector machine. And the biometric key is the highest confidence degree, which is the class of this particular hash vector. At the same time, it also takes the top n by 2 classes. If you think about it, if an attacker gets this particular classifier model, and he's trying to guess the key based on this model, the number of choices that he has is first to choose the topmost class, which is 1 out of n, so n, and a combination of nt, the NCT I call it. So if you calculate for n greater than 69, the number of choices for an attacker to choose a biometric key would be greater than 2 to the 64, which is the lower bound of what is considered computationally hard. Yeah. So we looked into some, we actually tried to get evidence if these algorithms work. So we looked into some thermal optical sensor fingerprint samples and iris samples. We also found some nice face samples. I mean, you can see the differences. One is very straight, very easy to recognize. The others are have a certain amount of noise. And the results were pretty reasonable in the sense that the thermal did better than the optical, as you can see. Then the iris did well too. In the case of the face, it was less than 2% of a change, even if we had more noise in the second set of samples. Then we also looked into the uniqueness and the repeatability. So I talked about the interclass and intraclass. So this is basically a ratio of the interclass by the intraclass distances. So the main idea here is that we need large interclass distances. Two different people should be very different from each other. So this number would be big if we had large interclass distances and small intraclass. So the same person is able to regenerate their biometric key at different instances. So we got some big numbers over there. Then the final set of results, a summary over here, is that we got biometric keys of length from 64 to 214 bits, depending on the number of classes that we had in the last classifier model. And we tried to synthetically increase the number of classes by adding some spurious classes. And there are some very interesting things here, because you can look, if you add random classes, then we try to see ways that an attacker can identify a random class from the real class and so on. So there were some interesting aspects here as well. But if we analyze the system a little more, there are a few most important things. We have the biometric image, which is the main biometric. Then the secrets that we have is a hashing secret to choose those squares that we saw while the hashing process happens. So there are some hashing secrets. Then we have the model, the classifier model. And from all this, we can generate the biometric key, and which is used with the commitment secret, the random R that we used to commit a particular identifier. So these are the main things that are there in the system. So if the biometric image is compromised, then we pretty much we can't do much without the secrets. So even if I can capture somebody's image and fool the system that I have a particular face, without the secrets, I cannot use the model to generate the biometric key. So I can't get to the key. But even if the model is there and the image is there, I cannot map a particular biometric to a point to say, okay, which class does this particular image belong to without the hashing secret. Another interesting aspect is what happens if all of this is compromised. If all of this is compromised, we still show that the process is one way. From the biometric key, you cannot go back to the original image, which is a very nice thing. Another thing is that if everything in your device is compromised, so you can consider the case where you store all your secrets in your laptop and the laptop is compromised. Then we show that without the biometric, you can't use all the secrets and all the information stored in the machine to actually regenerate the secret. So this is one of the main requirements. What's the point of having a biometric if everything is based on stored secrets? So this is one of those main cases. Okay. So at this point, I will go into the last aspect, which is to do with the history-based identifiers. So we looked at the main zero-knowledge proof protocols, which do the multi-factor verification. Then we saw how we have to play with the biometrics to make them fit well and use with the rest of the identifiers. So one good thing over there is that I'm not using the biometric or multiple biometrics together with each other, but also using them with other identifiers like social security number and so on to do this multi-factor proof. So it becomes a very flexible, scalable system. So now we also consider what happens if we are considering what you do. And the main idea here is to use the e-commerce and m-commerce activities. Does everybody know what is m-commerce? Nobody? Mail commerce? No, close. M is for mobile. So nowadays, people have really fancy phones and stuff, and you can do a lot with those. And the idea is that when you are using these mobile devices, you can use them just as an extension to e-commerce activities. So we were thinking that history should really be incorporating all sorts of activities, some that you do online, you're buying things online, but also maybe activities that maybe in future we go to a Walmart and are able to pay with this or get receipts on this and so on. So the challenges, the security challenges here is to be able to leverage these past transactions, either online or in person, as I just mentioned, to be able to establish trust with all this information. So you could use it for rebates, e-prescription, but then we also want some security and privacy properties to hold. In that, we want to make sure that the person who's claiming these attributes, history-based attributes, is the owner of these. So I don't steal all the information, the nice information that you have, and present myself as the person who did all this. Another thing is that this information should be in control, especially in cases of mobile devices. It's maybe easier to capture this information and somebody can potentially misuse it. So we want to make sure of that. Another thing is the availability. I don't think many of us can really prove to some shop that I really came here last semester and I bought books more than $300. Those are the things that is not easy to prove at this particular point of time. So the key idea over here is that we take this transaction history and encode it as electronic receipts. And the idea is to enroll these receipts at the registrar and have something called the receipt record, which is similar to the identity record that we had for credit card numbers and so on. So based on a very few simple protocols, by this time I thought everybody will be zoned out, but the idea is to understand how we could potentially add these receipts and how could we use them for certain kinds of transactions. So Homer again goes to eFollets, a website, and buys a book, and he says, okay, I want a receipt for this book. Then the service provider starts a session handle, which is denoted as the random. The next step is that Homer goes to the registrar. The registrar is the entity which is basically using, managing this information. So he says, this particular receipt record is mine. So he points out on that, and he claims ownership on a receipt record through multi-factor verification. Okay? So once he has strongly verified his identity to the registrar, he starts creating this row submit, which is another token with some session handle to say, okay, you can submit a particular receipt. So Homer goes, he takes this particular row submit, gives it to the service provider, and now the service provider creates a receipt of a certain form, creating based on the particular transaction, who's the seller, who's the buyer, so on. And he gives this receipt, which is passed on to the registrar. The registrar can simply add this. So, since there's a time, I can ask a question. Do you know what was the main reason why TJX got in trouble? Like the TJX case was the point where it was storing a lot of users' information, the driver's license number and whatnot. So they were storing all this information for a particular reason. Do you know that? It was basically storing this information so that if a person comes later and says that I don't have the receipt but I want to return this item, so the shop wants to make sure that it is the guy who actually bought the item. So when the person buys the item, it records the driver's license number and so on. So at the time of return, it can check if it's the same person. So this is too much information to store just because of this particular thing. So there are lots of solutions, very simple solutions that can replace the need to store all this information. Because what happened was that this information was compromised and now it's liable for a huge amount of money. I really don't remember exactly the amount, but it's reasonable if you check the news. But over here I show one particular case of how a system could be used to return an item. So here you don't provide any more information than the receipt which is recorded on that, or even if the receipt is not there, you can prove ownership on a particular transaction. So to do that, first what Homer does here is that he goes to the registrar, he verifies his identity using this multi-factor verification, strong verification techniques. And then he identifies this particular receipt. And the registrar gets ready. He says, okay, I'm going to revoke this eventually once you return the item and all that. So now what Homer does is when he's trying to revoke a particular item, he also proves ownership. Like if you see in step 2, a part of the identity record is given to Homer. This is signed by the registrar. So I have not provided too many details, but the idea is based on this identity record, what Homer can do at step 3 is to prove ownership on that receipt and saying that I am the guy who has bought this item earlier. And he does this in zero knowledge fashion, so not more information is revealed than what has been recorded. Then they want to make sure that there is fairness in this whole transaction. That means that if Homer goes and returns the item, we don't really trust the service provider, so we don't want the service provider to run with the item and not provide the refund. So we want the return, the refund, and the revocation of the receipt all happen simultaneously. And that's why we use a simultaneous contract signing. As a next step, when, as per the contract, when Homer goes and returns the item, basically the service provider provides a refund token, which really provides F, which is a refund, and a revocation token, which says that this particular receipt needs to be revoked. It's encrypted with registrar's key, so at step 7, the registrar gets it, and it revokes it and gets the refund back to Homer. Okay, so we had those protocols at an online version, and more recently what we did was, okay, now what happens if you're just having these little devices, our cellular phones with us, and we had to do something like this in an actual physical location. So one would think that the challenging part is, okay, how much can I store, how many receipts can I store, and also most people think that zero knowledge proofs take a long time, and it's potentially, so most of the phones nowadays are good enough, and I'll show you some figures that we can do multi-factor proofs using such devices. So as you can see in this example, Homer goes and does this online e-commerce transaction, and as per the earlier protocol, it can add a receipt, and a step that I didn't talk about was that you can take these receipt attributes and you can extend them. And basically what you can do is to create some cryptographic commitments of these receipt attributes. And basically the idea is that once you do the cryptographic commitments, then you can prove that you have a receipt attribute without showing it in clear. So if you want to do that, then you extend a particular receipt attribute. So Homer goes, he uploads the receipts, and he goes to an actual physical location. So say he goes to Follett's store, right? Not E-Follett's. And over there, say if there's a policy which says that if you've bought a book for greater than $80 from the online or in person, it doesn't matter. So if you have a past purchase of greater than $80, then you can get a particular discount. So to do that proof, we find a way to construct the proof on the phone and provide it to the service provider. And if this proof can be verified correctly, then he gets a discount. So the case is as simple as that. When we implement, yeah.
Is it true that every textbook that Follett sells is greater than $80?
I think that is the case. It's been a while since I haven't bought my own books. Yeah. At some point when you're in grad school, you start getting books from all your seniors and you don't go to the stores anymore. That's a good thing about labs, huh? So when we were implementing this, on the web-based system, there are three main components. We have the registrar, as we talked about. Then in this registrar, the main thing is really just the database where you're storing all the identity records and all that. Identity records and receipt records. We built it on top of the GridSphere portal framework, which is very stable and it provides a good way to extend it. And on the user side, things are very light because you don't have to install any software, because most of the proof creation, commitment creation, they all happen using the applets. The main thing that is really important from the user end is to be able to manage secrets. So we created something called the wallet, which is managed on the cellular phones or on the laptop. But this is the one key thing which needs to be taken care of on the user end. On the service provider end, in addition to what all it has, it needs to have a verifier. So when it gets a proof, it needs to know what to do with the proof. So it needs a verifier component and a proof requester. So typically, service providers don't ask you for proofs. They ask you for your name, your address, your credit card number. So taking a step from that to asking really for proofs instead of the actual identifiers and clear is a big step. I think not so much as from the technical point of view, which we have explored, but there are other issues as well which need to be addressed. So this is the web-based architecture. When we start looking at the mobile phone component, which is mainly the user component, the applets which were highlighted are really done on what are called the phone midlets. So you have we really considered the Nokia phone architecture. So we can run it on top of the phone operating system. We also looked into what are the types of storage and how can we use the tags. There are lots of very interesting details and constraints on how we can use such devices and how they can interact with using their subcomponents with the readers of the service provider. So just a very quick look on how much time it takes. You can see on the x-axis is a number of identifiers that we are proving. These are the multi-factors, the number of factors. And so here you have one factor. Towards the end of the graph, you have about 50 factors that we are proving. And since we had those constant number of exponentiations, over here you can see even with the number of proofs, number of identifiers that we are proving is increasing, there is no significant change in the amount of time it takes to construct these proofs. So we can really take, for the applet, it takes less than 0.1 second, almost on a constant basis, to create multiple proofs. In the case of midlets, it takes not more than 2.5 seconds to create such proofs. Now, if I take this blue line here and compare it to the verification, just in a different scale, so it looks different. But the idea here is that the verification, the server side has a sublinear component where the amount of time it takes slightly increases. But even for 50 proofs, it takes about 0.1 second to verify a particular proof. So those were the main components that I wanted to mention. As a summary, what we really did was to look into a comprehensive solution to privacy-preserving multi-factor verification, which is one of the key components to prevent identity theft in identity management systems. I don't know if this point came out very clearly, but the main assumption here is that data breaches happen. There are so many ways that you just cannot control the compromise of such information. So at the time of use, if we have strong verification techniques, then we can prevent misuse of this stolen data. So you can have multi-factor verification techniques without jeopardizing privacy, and it can apply to various types of identifiers, as you saw in this presentation. So we provided cryptographic protocols for aggregate proof of knowledge, which was the main idea behind multi-factor verification, and we showed how performance, flexibility, and storage-wise they are they can be used for practical purposes. As well, we provide the algorithms to generate biometric keys. So this is a big research area on its own, but having reliable methods to generate these keys provides a way to use these biometric and non-biometric factors together. So you can use biometrics just as you could use your credit card or social security number, which is very nice. And we show how you can decouple also your actual biometric features from these biometric keys when it comes, and so that it addresses the privacy and some other security concerns. We also provided as evidence some empirical evaluation of our techniques. And finally, for the protocols for establishment and management of history-based identifiers, we showed how to ensure the security and privacy requirements of such history-based attributes. And the prototype implementations were especially fun because they were aspects which have to deal with the dynamism of identity, if you might, and the performance followed through from the cryptographic protocols that we designed. So I actually finished earlier, but okay, I have one more. So future work, I think there might be some students here who are looking at, who are not done yet. So there are a lot of applications of such verification things. So the VeriIDX system, which is really what the whole thing is called, is being used right now. We're looking at applications in healthcare and finance, and the various technical aspects related to, say, the aggregate zero-knowledge proofs. We're looking into some interesting extensions of such things. For example, we didn't consider threshold aggregation. For example, if I want to prove that I have k out of n identifiers are correct, so can I do that? And it's a hard problem. It's a hard problem in zero-knowledge proofs. Similarly, multi-party proofs. If a bunch of friends want to get together and want to prove something together, then doing this multi-factor in a zero-knowledge fashion without really exchanging each other's secret is a very interesting problem in its own. As far as the biometrics are concerned, we are trying to look at extended use of these biometric keys. Like how I use the biometric keys was very specific to what we were doing, but if you had to use the same keys in your real ID, in your passports, or just to encrypt files in your computer, then there might be other aspects as well that we have to consider. And also we're looking into how error correction and machine learning techniques can be used to make these biometric keys much more reliable. In addition, we have this history-based identifiers really do go into the profiling and other aspects which is related to insider threat, fraud detection, and areas of that kind. And over there, my aim was to find some kind of a balance between what information is collected about you and how it can be used for fraud detection and all. And also the mobile identity. Going into the domain of mobile phones and mobile identity itself, there are a lot of interesting applications that one can look at. So that's about it. If you have any questions, you can ask me now, or you can email me later if you think about it. I wanted to put Happy Halloween here, but this thing won't compile. There's a lot, I know, but if there's anything in general also, because the whole thing was motivated from identity theft and what are the real problems, and then again switching to technical solutions, of course.
Any questions? Thank you, Evan.
No problem.